All right, in this video, we're going to tackle the concept of using partial fractions to help us deal with integrals. Specifically, partial fractions is not a calculus concept, it's an algebraic concept, but you're going to see how we can use it to attack integrals involving rational expressions. Before I get into the details of using partial fractions, what I first want to do is review a concept that's been kind of coming up since we've talked about substitution, and I really want to hit it here to make sure that we can use this moving forward to make our lives a little bit easier. And what this is about substitutions involving simple inner functions. Specifically, I want to talk about when our inner functions are these linear functions right here. In this case, you would look at this and hopefully realize a good u substitution in this case would be u equals 2x. The thing I want to emphasize, and again, have emphasized before, but really want to hit it here in this video at this point in Calculus 2, is to say, when I have a linear substitution, there's no interesting work really with the differentials. I just get this constant factor. In this case, I get du equals 2 dx. I like dividing this constant over to get 1/2 du equals dx. Importantly, when I have a linear substitution here, I don't get any variable parts out. I just get this constant factor that will influence the end result, but doesn't have anything to do really with the substitution. In fact, I do a straight substitution with dx and du, but I get this 1/2 on the outside here. So if I put this all together, I'll have that 1/2 out here. And now I have the cosine of u, and I swapped out my dx for du. And then after doing that, it's really straightforward, right? I'll just get 1/2. The indefinite integral of the cosine is sine of u plus c. And substituting now back in for my x so I can get my final answer in terms of x, I have sine of 2x plus c. The point I want to emphasize here is this 1/2 and how this came out. The 1/2 comes from this substitution, but how I think about it, how I think it can be useful and quick for you, is think about this, again, in terms of a linear, this is easy. We're doing the anti-chain rule. So this factor right here, I think of the anti-chain rule. When I want to integrate, cosine of 2x, I know I'm going to get the sine of 2x, but I'm also going to get this 1/2. And the way to think about this is, again, the reverse of differentiation. I know when I differentiate this, I'm going to get cosine of 2x, but then also I'm going to get this factor of 2 out because it's the derivative of this linear factor. When I'm integrating, I'm just doing the opposite. I'm going to be dividing by that factor here. That is the derivative of the inside. I've already emphasized it probably too much, but I want to say this move is only really suggested when you have linear inner functions. And if you can identify those linear inner functions, it's always just the constant attached to the variable that you're going to be dividing by in this case when you're integrating. Again, dividing or multiplying by the reciprocal, because that's the opposite of what would happen when we use the chain rule. And so then just to follow it up with these two examples and to show you how we're doing this. Again, when I look at this right here, I see this 5x plus 1 as this inner function put into this denominator. I'm thinking of this as 1 over u, specifically where u equals 5x plus 1. What this gives me, it gives me this factor of 1/5 if I was thinking about the integration part. And so doing this, and again, this might be a bit of a step for you, but I want to show these to you and try to encourage you to use this maneuver moving forward. I'm looking at this, and again, there's nothing, this is simply just a linear down here. I'm thinking of this as 1 over u, and then when I integrate that, what I get is the natural log of the absolute value of u, which in this case is 5x plus 1, but I need to take care of that 1/5 factor right there. So that's an example of me using that mental substitution move. And again, I don't think there's anything wrong with doing this and then verifying that work with like the u substitution, but I do think that doing this quickly will make your life a whole lot easier. In this example right here, I'm going to do exactly the same thing. Again, my thought is I'm going to let u be this inner linear function right here of 2x plus 4. So I have that, giving me the fact that this Reverse chain rule factor would be 1/2. Again, it's the inverse of this, or dividing by that coefficient right there in front of my variable. And so when I integrate this, I will think of this as u to the third. And so I'll get 2x plus 4, or u to the fourth, divided by 4. So that's the anti-power rule. But then I'm bringing in that reverse factor of chain rule. I need a better word for this instead of reverse. Inverse factor, whatever. Hell, it's the opposite of multiplying, right? I'm dividing by 2 because if I applied the chain rule to this, I would get out a factor of 2. And then just to clean this up real fast, I would get 2x plus 4 to the fourth all over 8 plus my constant of integration c. As we move forward in these videos, we're going to use this mental substitution with these linear factors more, just because, as you know, we're going to be looking at more and more complicated integrals. That should be really obvious at this point. I mean, you've gotten through substitution, integration by parts, and then recently you dealt with trig substitution. And so what this is going to do is try to take a little bit of a load off, especially with what you're writing. And if you can identify these pretty quickly, and now it gets a little more difficult, but then you see this as 1 over u, or u to the third is a key component to this. And as you'll see in the examples that I'm going to do in the rest of this video, I'm going to use this trick multiple times just to make my life a little bit easier, because I'll have done so much work to set up the problem that I don't want to use multiple u substitutions for each of the integrals I'll be evaluating. All right, now to get into the fun of playing with these partial fractions. Importantly, before I start again, I want to say 2 things. First, partial fractions is not a calculus technique. It's simply an algebraic technique. So you're going to see all of the work, interesting work I'm going to do here is not calculus based. It's simply just algebraic work. If you haven't seen these before, it's not that crazy, but you'll see there's an important setup that we're going to use. But I also want to say this. So second, I want to say, we actually have methods for working with integrals like this and not this. And the specific reason here is because this denominator is something that plays nice. Specifically, what we would do with this, and I won't do this work, is we would take this and we would split this integral up using this idea that this is a fraction. We have these numerators. I would write it like this and like this. So adding these 2 fractional pieces here, why this works in this case is I can use substitution for this term right here. And this is the derivative of tangent inverse, right? And so I actually can take this integral. That's not the case with something like this. We have a more randomized denominator. And then as I do this, it's important this technique of partial fractions is useful when the degree on bottom of your rational expression is higher than the degree on top. So if our degree on top was the same or bigger, we'd actually use long division, and you'll see examples of that. But in this case, partial fractions is used when the degree on bottom is bigger than the degree on top. All right, here we go. Let's attack this problem. And again, most of my work's going to be over here on the side in pink. It's just going to be my algebraic work. You'll see once I've done most of this, the actual calculus work is pretty straightforward. First things first, what I'm going to do is I want to break up this expression into multiple terms that have simple denominators. That's a really important move with this partial fractions. The first thing to do is I want to factor this denominator. So I'm going to do that right here. This becomes x plus 2 times x plus 3. So over here, I'm going to write that as my denominator. Then what I do is I'm going to say that this expression right here is equal to 2 terms being added together that take each of these linear factors. So the setup is I have one term right here that has x plus 2 as a denominator, and then I have another term here that has x plus 3 as a denominator. Importantly, when you do this, each of your linear factors, so you factor your denominator into linear factors, each of those linear factors gets represented by one of these terms. In the next example, you'll see what happens if we have duplicates of the same linear factor, but we don't need to worry about that right now. What I'm going to do then up here, these are going to be constants. So I can break this down or decompose this into these terms where I just have numbers on top. And that's a beautiful thing. I'm going to just give those constant values right now of a and b. My goal then with the work that I'm doing is to find these a and b values. All right, so I've set it up. What I'm going to do now is play with this expression. Again, my goal is to find these constants a and b. First thing I'm going to do is multiply both sides of this equation by this denominator right here. So I'm going to multiply both sides. I should write this separately of this times this and this, but I'm running out of space over there a little bit. So you know what I'm doing here. I'm multiplying both sides of my equation by this right here. What effect that has is it simply cancels out this denominator on this side. So I get x minus 4 on this side. Over here, when I'm multiplying these terms by this, the x plus 2 cancels. What I end up with is a times this x plus 3. So I get a times x plus 3 here. And then you can see what happens over here. This just becomes b times the x plus 2. Okay. That's the first big move. Then what I'm going to do is I'm going to distribute these and I'm going to combine my x terms and my constant terms. To give you an idea of what we're doing is I'm going to get these expressions with an x term and a constant term, and I'm going to use the information of what this is equal to over here to find those a and b values. But that goes like this. So I get x minus 4 equals ax plus 3a plus bx plus 2b. Then what I'm going to do is combine like terms, again, specifically these x terms and these constant terms. It's important to rewrite it like this to help you set up the work we have right after this. So x minus 4, ax plus bx is a plus bx. Again, you could think about just adding like terms, right? You also can think about putting these together and factoring out the x. It's exactly the same way of thinking. And then 2a plus 2b. I'm going to write it like this. 3a plus 2b. Again, because I want to think about this as my constant and this as my linear factor right here. So what we do with this is we then are going to set up a system of linear equations. Specifically, again, this a plus bx, for this expression to be equal to this expression, this coefficient in front of x has to be the same as this one. And we can write this in, we don't need to, but it's 1x, which means that a plus b has to be equal to 1. And then also this 3a plus 2b component has to be equal to negative 4. So the system of linear equations that we need to solve is when a plus b equals 1 and when 3a plus 2b equals negative 4. It's probably just me at this point. I get a little giddy excited when I go back to these old algebraic moves that I haven't used for a long time. Just to remind you about this, you could use substitution, addition, elimination. I'm awkwardly excited about addition, elimination. In this case, let's eliminate the b's. Doesn't really matter, but I'm going to multiply this first equation on both sides by negative 2. What that will give me when I distribute that through is negative 2a minus 2b equals negative 2. Down here, I have 3a plus 2b equals negative 4. And then what I'm going to do is add these together. When I add these together, I've eliminated the b's, which I was trying to do. 3a minus 2a is a equals negative 6. Then once we know that a equals negative 6, all we got to do is go back to one of our equations to find out the b value. In this case, if a is negative 6, I won't show this work, but you could verify this on your own. If I have a negative 6 here and I'm solving for b, I would just add 6 to both sides to get that b equals 7. Okay, that was the whole partial fraction part. I just want to quickly review that so you can see the steps. It might look a little bit convoluted. It's not that difficult once you get the method down, especially when you know how to go from this step to this step. But all I did was take this, I factored my denominator into linear factors. Then I have these terms over here where each linear factor is being represented in these denominators. I use any kind of values here, usually use A, B, C, D for these terms up here. These will be constants. What I do then is I multiply both sides by that denominator. I'll get something always that looks like this. My job then is to distribute, do any kind of algebra I needed to do, and then distribute these constants through. I group them by term. So x squared terms, x terms, constant terms into this case right here. How I go from this step to get to my system that I'm solving, it's like a separate side problem, is that I say, okay, in this case, if these expressions are going to be equal, it means this x term and that x term have to be identical, meaning A plus B have to equal that 1. And also this constant work without any variables, that has to be -4. So then I'll have 1x minus 4, so it's equal to this side. That gives me this system of linear equations. And again, if you're like, what the heck happened right there? I'm sure you've seen it. Just Google search or find any notes you have for system of linear equations. Solving that gives us this. What that tells us are the values for A and B in this original problem. So what that means is, going back and actually now doing some calculus, is that this expression right here is exactly the same as -6 over x plus 2 plus 7 over x plus 3 dx. And then we know we have these terms. I can split these up individually. I don't have to actually write this out. I can just know I can integrate them separately. But just to show all the steps here, this would become -6 x plus 2 dx plus the integral of 7 over x plus 3 dx. In each of these cases, I would factor out the -6 and the 7. And in fact, I'll rewrite this real fast to show that. Finally then here, this is why I started this video with this mental substitution. What I could do now in each of these cases, like here, I could let u equal x plus 2. But because this is a linear factor, I don't actually have to physically do that substitution if I feel comfortable with it. Again, if u was x plus 2, then du would be exactly the same as dx. So I can think of this as 1 over u. And there actually isn't this factor, this reverse factor of chain rule that I need to worry about. If I think of this as 1 over u, with the x plus 2 being the u, what this integral would come out to be is -6 times the natural log of x plus 2 plus c, but I can just add that on at the end here, plus 7 times the natural log of x plus 3. I just did exactly the same mental substitution there, but since that coefficient in front of the x is just a 1, nothing really interesting happens. And then plus c. So again, the method of partial fractions is not an incredibly deep calculus concept at all. It's actually an algebraic process. The hope is you've seen it before. Maybe you didn't love it or become an expert at it. If not, it's not really a big deal. This is the basic concept. I'm now going to show you an example where I have actually 3 factors, where one of my factors is actually duplicated, right? So I have some linear factor squared times another factor. You're going to notice it's a little bit more complicated, but it's all exactly the same idea. The idea is in the next example, we're actually going to get a 3-variable linear system with 3 equations, but we'll talk about how to solve that. That's about as deep as these problems are going to get for you.